Okay, can we? Hello. Well, we are starting our second semester of, how we call it, Английский по специальности. It's not English as major. How would you call this? I forgot again. We invented how it's called last semester, but I forgot. So this semester actually will be, we will continue the same line as the first semester, and I plan to tell you the contents of the unwritten second volume by Koch, of the planned second volume by Koch. Okay, to cover some of the material from his first volume that was not covered last semester, to finish the topics we discussed last semester, and then to discuss several new topics in the same style to sort of finish the very general outline, the very general picture of the classical mathematics, the mathematics of the 19th century. So the topics I plan to cover in this semester are roughly as follows. First of all, well, last semester we covered number theory, algebra, and complex analysis, essentially. Okay? Nothing else, yeah? Right? So there are still a lot, you remember that. There are still a lot of subjects that we haven't covered, okay? And we haven't even finished what I promised the last semester, namely some of the most interesting meromorphic functions, okay? Like, I would like to start telling you about, today, actually, about elliptic functions, modular functions, because these are actually, these are very hot subjects now, because they were very hot subjects in the 19th century, then they were forgotten out of, how you call it, out of fashion, I would say, for a number of years, but they are very hot subjects again, for instance, well, in connection with number theory, of course, and algebraic geometry. But they are interesting in their own right. And then I would like to cover some maybe Riemannian geometry, okay, up to, well, I don't know whether I would like to cover that all, but at least maybe to mention, because that's a 19th century problem. Of course, it was only solved in the 20th century, the classification of symmetric spaces, okay? But it's a typical 19th century problem, okay? But of course, it was only solved by Elie Cartan in the 1920s, but it was a major subject of a large part of the 19th century differential geometry. Okay, spaces of constant curvature. And then the third subject that I would like to cover, of course, would be the, in connection with this, the Lie algebras and Lie groups. Okay, because that's actually the another major breakthrough of the 19th century, which determined a large part of development in the 20th century. Okay, and also a huge part of applications of mathematics in the 20th century to physics and to other fields was dominated by the theory of Lie groups and their representations. Okay, that's another major sort of core subfield of mathematics, which became a core subfield which became central for a huge part of mathematics in the 20th century, but which has its roots in the 19th century, and in particular in solution, explicit solution of systems of differential equations. Okay? So the Lie theory actually arose from the attempts to solve explicitly systems of differential equations. Okay, and then 4, I would like to speak about harmonic analysis a bit, but just a bit because, well, in connection with this, because if you look at these subjects, they sort of, each one of them is attached to the next one. Okay, but of course, then I would like to discuss the 19th century algebraic geometry. So it's not the whole picture of the 19th century mathematics, of course. At least some of the key fields are missing, as you noticed, like partial differential equations and probability theory. I'm not really an expert on that. And it's not that these are very, very venerable fields of mathematics. And of course, they also, the 19th century developments were extremely important, but I don't think I really will have any time to cover this. But this is more or less the plan for this semester. But since this is an English lesson, I would like to start with today, maybe before we pass to elliptic functions, I would like to start with some English. Here I found a glossary of common mathematical terms by Stephen Kranz, which is very, very useful. And also a description of methods of proof by Richard Green, I think, which is also very useful. But glossary of common mathematical terms, and you tell me where to stop. This is, well, you know, in each, in many fields, in many, how you call it, occupations, beruf, the many professional activities, people use their own language. Like when you hear people say in, I don't know, in woodworking or metalworking speak, you won't be able to understand half of the words they use. Okay? And of course, the same applies to mathematics. And so it's very useful to have a dictionary or a glossary that translates common mathematical sentences to the everyday English. So this here is a very brief glossary of mathematical terms. So mathematics usage, and then common language. Okay, so first, this is trivial. While in the common day English, it means I forget the proof. Have you seen that?
Have you used it?
Well, of course, I use it every day. Yeah. This is obvious. Do you know the translation?
Is it wrong?
No, you forget the proof. Well, this is a calculation. Let's all forget the proof. Well, clearly, well, the author says it's obscurely, etc. You got the idea. Well, read my book. I don't know. Well, let's have a joint paper on that. We are equally famous, but I am lazy. I thought about that question 20 years ago, but I forget the answer. I'm more famous than you are. That's the most insightful question I've ever heard. Let me think about it. You are more famous than I am. Well, and so on. That problem is intractable. I can't do the problem, so neither can you. Well, I don't understand that step. You goofed. How do you reconcile your theorem with this example? You are dead. Your theorem contradicts my theorem. I am dead. Well, and so on. This is Steve Krantz. Okay. And here is another list of proof techniques that is very, very useful. And here you will learn some words. But this is, you should use this, actually. Well, you know, Linik used to say, obvious, he said, he was saying something like, obvious meaning that it's obvious how to prove it, something like that. Nothing is obvious unless you have a proof. So, methods of proof. There are 24 or 25 of them listed here. I won't list them all. I just name the methods, and then without defining them, it will be clear from examples. So proof by example. Proof by intimidation. Well, that's a very useful technique. You know what's that? Proof by intimidation?
Use lots of complicated words that no one can understand.
No, but can you give an example of such a proof? Proof by, well, that's also a very useful technique. By vigorous hand waving. Okay. Proof by cumbersome notation. Well, I do not like this one. But many people use it, actually. Yeah. Okay, well, the other two are typical. Proof by exhaustion. Proof by omission. And proof by picture. And there are many more. I will mention more. But can you guess what it means? Well, you want to prove a theorem for any dimension, you prove it for dimension 2, and say, well, the general case is similar.
It proves that all people have the same color of their eyes.
Well, that's a known thing, yeah. I mean, all horses are of the same color, yeah. Of course. Proof by intimidation, well, it's essentially this. You say trivial. It's trivial. And then no one can, it's obvious, but no one can ask why it is obvious, you know, because they feel ashamed to ask, yeah? This method of proof works very well in the classroom, and even better in the seminar room, right? Well, the next one, it's clear what it means. You just use as many different alphabets as you can, so that after a few pages, people start confusing letters, you know, and but they cannot say that the proof is wrong, because how can they? Well, proof by exhaustion is that you publish two papers that are 150 or 200 pages long, and by the end of the second paper, no one really knows whether you have your results proven or not. Okay, because then you've stated the result in the beginning of the first part, of course, and by the time when the second large paper is published, no one knows. Everyone then will refer to your theorem as proven, even if the third and the fourth, how you call it, parts of your paper will never be published.
That sounds like the proof of the ABC theorem.
The proof of?
That sounds like the proof of the ABC theorem.
Well, it's a combination of different proof techniques, yes, actually. The proof by omission goes as follows. The reader may easily supply the details. Also very, very useful. And the other, well, it says 253, usually something like 500 or 600 cases are analogous. And that's not a joke, actually. Most of the proofs, say in algebraic topology that I've seen, in the actual papers, in the published papers, they look like that. They draw some diagrams, some pictures, they sort of treat some 4, 5, 6 cases, and then say that the remaining 500 or 600 cases are similar. Okay, and these are actual published proof of accepted theorems. Okay, proof by picture, of course, works well in combination with any of these. Yeah, it's or proof by example. Okay, you just draw a picture and says that you can see it all from the picture, and well, but there are many other methods of proof, like proof by obfuscation. You know what's that? Oh, that's a very useful technique. Very, very useful. Do you know the word? Obfuscaция in Russian. Well, there's a special field actually in computer science, in theoretical computer science, the obfuscation of computer programs. So that you write a computer program in such a way that no one can use any part of it unless she buys the whole product. Okay, so it's you write the code in such a way that it cannot be sort of decompiled and used in any other product. Proof by obfuscation. So you accompany your theorem by a long sequence of unrelated or vaguely related sentences that use the same word, the words essentially, but otherwise they are sort of grammatically correct, but meaningless. It's very, very useful. Okay, but these are, so to say, the ways of how you prove by the methods of proof that use, meaning. But otherwise, you can refer to the social phenomena. Like there is a very useful proof method by funding. How could 3 different government agencies be wrong? So if they have funded your research, Well, if someone had, actually. That's already a proof. Proof by eminent authority. Well, I saw this and this in an elevator, and he said it was probably okay. Proof by personal communication. Well, someone has written in a letter that something holds. Proof by reference to inaccessible literature. Well, now it's less common, but it used to be very common before. To refer to preprints that, but actually today, Alexei, before the lunch, Alexei has mentioned another method of proof by forward reference. You refer to the paper published in 2020. Okay, so a reference to a forthcoming paper by the author, which is often not as forthcoming as at first. Okay, and we know such examples. Actually, I've told you last semester, I've mentioned, I think, the paper by Georg Cantor on the continuum hypothesis, where he said that the proof was forthcoming for Setzung folgt. So how it's in English? To be continued. It never was. Okay. But if you believe, I mean, you can refer to the proof by meta proof. Very useful. A method is given to construct a desired proof, but it's never implemented. Proof by mutual reference. In one paper, you refer to the result from the other paper, and in that paper, you refer to the, to the proof by importance. A large body of useful consequences all follow from the proposition in question. Have you studied philosophy, by the way? Have you discussed the proofs of existence of God?
Quite a lot.
Have you?
Quite a lot,
yeah. So these are proofs by cosmology. The negation of the proposition is unimaginable or meaningless. Okay, these are typical proofs of the existence of God. And the most important method of proof by miracle. Okay, so I think that was that for the mathematics terminology. And so now we can pass to the elliptic functions. Okay, so I will assume that we remember Riemann's theory of functions, of complex functions. Okay, so what's the elliptic functions? And here I would like to philosophize a bit, actually. Namely, many young people believe that sort of the core of mathematics are general theories. I don't think that's the case. Actually, I think that still the basic examples are still there, and the general theories are just different ways to look at these examples. Okay, but the fundamental thing, the fundamental object of mathematics are these examples, are these objects that exist, these things like, think of something like Bernoulli numbers. They were introduced to some the initial the powers of the initial interval of or the natural numbers. But then in the 19th century, they occurred over and over. Well, in the 18th century, after that, they occurred, say, in the Taylor expansions. In the 19th century, they occurred in Kummer's work on the proof of Fermat theorem and so on. Think of something like, well, thinking of this building, of Chebyshev polynomials. Okay, of course, the first definition you see is when you wish to express cosines, say, or sines of multiple angles in terms of the cosine and sine of the original angle. Okay, that's how you see the Chebyshev polynomials of the first and second kind first. But then you discover that, and of course Chebyshev himself discovered that, that you discover that they also answer very natural problems about approximation or something. They have some minimal properties. And then, say after some years, this was what was discovered by Reed. I don't know whether you know that. Have I mentioned that already or not? What are the systems of polynomials that are commuting with respect to the composition? Do you know Reed's theorem? Ah, no? Actually, you should answer. Reed. No? Well, you ask what are the systems of polynomials, okay, say polynomials of infinite systems of pairwise commuting polynomials. Do you know the answer?
I know such a circuit.
Huh?
I know an example.
Yes, what's the example?
X to the power of n.
X to the power n, yes. Right, that's one.
X minus 1 to the power linear. No. Linear
Huh?
x plus c. Or linear.
Well, of, say, of growing degrees. Okay, yeah. Well, of course, there is an obvious example that it should occur to all of you. For any polynomial, you take the power of this polynomial with respect to the composition. Well, but these are trivial examples. There is essentially one non-trivial example of such polynomials over, say, an algebraically closed field of characteristic 0. There is one such example. You know which one? Chebyshev polynomials, exactly. Well, up to a linear, up to a scaling, up to a linear variable change. These are the only examples over a field of characteristic 0. That's exactly the Reed theorem. So have you got my point? That actually these classical examples, these classical objects that occurred in one context, if they are really classic, this means that they have a lot of meaning. They have a lot of meaning beyond and outside the context where they originally occurred. Okay, and a large part of training of a professional mathematician, which was really sort of seriously neglected, I think, in the standard mathematical curriculum, very seriously neglected, is to acquire familiarity with these examples. There are not so many, actually, of these classical objects in mathematics, but they occur over and over in various contexts. And so the elliptic functions are another such examples, which are actually they were in the core of a large part of the 19th century mathematics. They occurred in the context of calculating, arc lengths of curves, but also in the context of calculating the integrals of algebraic functions. But then it turned out that they were of crucial importance in the theory of complex functions and in algebraic geometry. And then they are closely related to other very important classes of functions which are crucial in number theory. Okay, and this is one such field that was, it dominated the mathematics curriculum at the late 19th century, but then eventually it was falling out. And now, at most universities, even at mathematics departments, people do not study them. Okay, but of course, the core part of the theory is as elementary as you can imagine, and you could, in principle, study these functions at school, as you do study trigonometric functions. So these functions, elliptic functions, are in fact higher analogues of trigonometric functions, nothing more. Okay, and in the initial approach, in Jacobi's approach, they occurred exactly like that. So what are they?
So that's why they call it elliptic.
Oh, because they are called elliptic because they are related to the calculation of the ellipse, of the arcs of an ellipse. You will see it now. Originally they occurred like that. Of course they occurred in the work of Legendre and Gauss and were systematically studied by, in a sense, such integrals were, elliptic integrals were systematically studied by Abel, and the theory of elliptic functions in general was created by Jacobi. But the theory we use today, mostly the people who are algebraically oriented and not computationally oriented, of course we use the theory, the Weierstrass theory. Okay, so but first, what are they? Well, let's consider functions, complex functions. Okay, well, at school we have seen, we are looking at real functions which were periodic. Of course, you can also look at complex functions that are periodic. So at functions for which f is called simply periodic, if there exists an omega in C such that for any z in C, f of z plus omega is equal to f of z. Okay, and of course you know the examples of periodic functions. Okay, something like cosine of z. Or actually for us, it will be more fundamental the sine of z. You will see now, because for elliptic functions there is one sine but two different cosines that correspond to one sine function. Okay, this period is called fundamental if no submultiple of that, submultiple? Do you know what's a submultiple? So omega is called fundamental if no submultiple. Well, when you say multiple, you usually mean, well, you can mean a scalar multiple, but you usually mean a multiple by an integer. Okay? So that's a multiple, and that's a submultiple. So divided by an integer. If no submultiple of omega is a period. Well, of course, any multiple of a period is a period itself. Okay? So fundamental period, and of course the two fundamental periods, well, so Jacobi asked, are there doubly periodic functions? Well, these functions are holomorphic, actually, entire functions. Of course, we will see now that it's pointless to ask about holomorphic doubly periodic functions. You should at least allow poles. You should look at meromorphic functions, not holomorphic functions, by Liouville's theorem, right? Okay, so Jacobi asked, are there doubly periodic functions? Well, meromorphic. Well, we should think of the following fact. Jacobi still didn't have the advantage that we have. He was not familiar with Riemann's theory of complex functions. You know, at his time, the Riemann's existence theorem was not still established. Okay? So, Jacobi asked, are there doubly periodic functions? So, functions for which there exist two fundamental periods so the periods that are not multiples of smaller periods, right? Such that f of z plus omega 1 is equal to f of z plus omega 2 is equal to f of z. And what is obvious is that no such functions, except for constant functions, do not exist when omega 1 and omega 2 are, when their relation is real, right? When this guy is real, okay, no such non-constant functions exist. Well, obvious, right? You know why? Because, of course, if they are if this relation is real, it must be irrational, right? Because if it's rational, this means that they are commensurable. This means that you know, Z is a principal ideal to me. So if they are not commensurable, this means that this guy is irrational, and so this means that actually the function is constant on a dense subset, so it's constant, right? So this means that this guy must be imaginary. So this means that we select two periods omega 1 and omega 2, and this is 0, on the complex plane. And of course, any linear combination of periods is a period itself. Any linear combination of the fundamental periods is a period itself, right? So let's consider the lattice generated by these guys, okay? Well, you consider their sum and their multiples and their, all linear combinations. Okay, m omega 1 plus n omega 2, and n in z. Right, and any guy here is a period. So this lattice is called the lattice of periods. Okay, and a function that is meromorphic and doubly periodic with respect to a certain lattice of periods is called an elliptic function corresponding to that lattice. Okay, f is elliptic corresponding to the lattice gamma if one f is meromorphic, and two, f is periodic with respect to all omega and gamma. Okay, that's the definition. But of course, once you define something, the first thing you want to know that these guys exist. Right? But of course, as I mentioned to you last semester, Jacobi was already aware of the fact that examples of these guys exist. These are exactly the guys that occur in the as inverses with respect to composition of the values of elliptic integrals. Okay, so first, maybe before passing to the modern approach, well, modern Weierstrass approach, I will I will describe you the approach by Jacobi. So first of all, let's denote well, of course such functions exist. Constant functions. Okay, let's denote by m of gamma. Well, this is fancy m, the Fraktur, German m. Well, it's very easy if you do it in Tech. Should I write something else? Should I write simply k of gamma or something? What would you prefer, to see this or to see this? Well, m, of course, refers to meromorphic. K refers to Kuiper. Well, what you would prefer to see on the blackboard? But you know what I said now by using this notation. Yeah, what? That elliptic functions form an extension of the complex field. Okay, they form a field. The field of elliptic functions to the lattice. gamma. Okay? So they form a field. And of course, this field is an extension of the complex field because any constant function is a meromorphic function, is a periodic meromorphic function. Doubly periodic meromorphic function with respect to any lattice. Okay, right? So this is an extension of C. Do you see the connection with what we were discussing last semester? And of course, well, this was before Riemann, but if you look at this after Riemann, you see the following. You see that actually you can consider the Riemann surface C mod gamma, right? That topologically, all of them look the same. Topologically, all of them look the same. But this doesn't mean that they look the same as Riemann surfaces. We discussed that. The fact that there is a homomorphism doesn't mean that there exists a complex isomorphism. Right? Okay, and then elliptic functions, by being periodic, of course, they cannot be considered, they can be considered as functions on this Riemann surface. Right? So elliptic functions are meromorphic functions on C mod gamma. Okay, but they are so for us. They were not that for Jacobi, of course, or his predecessors. Okay, because they were not still familiar with the notion of Riemann surface, of course. Right? Okay? Huh? Exactly, yes, until Riemann's thesis, yeah, right, exactly. Well, so for them, it was a problem to describe the structure of this field. And in fact, this was done already by Jacobi, although we nowadays, use a much simpler description by Weierstrass. But of course, Weierstrass had the advantage of being able to use Riemann's existence theorem. So he knew that such functions are described by their poles, zeros, and multiplicities of those. And he knew the restriction under which comes from the fact that these guys are Riemann surfaces of genus 1, so compact Riemann surface of genus 1. Okay, and that's the only restriction on the existence of meromorphic functions. But of course, as I said, Jacobi was not familiar with that, so he had to construct such functions in some way. So how he did that? Non-trivial such functions, non-constant. Well, assume that you consider that you are familiar with integration. Well, very possible, but not familiar with the usual circle of functions, with the usual trigonometric functions, sine and cosine. Would you be able to discover the usual trigonometric functions? What do you think? Well, yes. If you are if you push hard enough, at some point, you will be willing to calculate the integral such as, for instance, the integral of from 0 to x of something like dt over 1 minus t squared. Right? Have you seen such an integral at your first undergraduate year? Or maybe at school. I mean, at school, yeah? Right. So you know what's that. Okay, well, that's u. But now the interesting part is how you, well, as a function of x. And so now you wish to express, of course, you wish what is called to invert this integral. Invert this integral. Inverting an integral, yeah?
It's right.
Inverting an integral means express x as a function of u. Okay? Okay, and you discover that x is equal to the sine of u. Well, if you introduce the notation. That's how you introduce sine if you were not familiar with that before. That's, by the way, one of the easiest ways to introduce sine. Right? Okay, after that, you define cosine, and it's easy to see that this function is odd. So, well, you know, functions are odd or even, yeah, right? Which will be very fundamental for elliptic functions, by the way. Because the basic function we will construct will be even. So we will construct with Weierstrass. Of course, and actually the odd functions are more fundamental because by squaring an odd function you get an even function, right? So it's enough to construct even functions, but odd functions, but it's not enough to construct even functions. So actually Jacobi started with an odd function. Sine is an odd function. But after that you construct cosine from the equation sine square. Alexei, here I'm solving your problem of putting exponent to the right. Plus cosine square equals 1. Right? And after that, you can develop all trigonometry at the moment when you discover the addition formulas. Because the structure of the field of trigonometric functions is described completely by two theorems, by this result, but of course for us it's the definition now, and by one formula that expresses addition theorem for sines or for cosines. Okay, so now you need one more theorem. You need the theorem that says cosine of x plus y is equal to, express this in terms of sines and cosines. And that's the only equation from which all other trigonometric equations follow. This is what is called addition formula. All right? And Jacobi, of course, was very much familiar with the work of Legendre, well, starting with Euler, as I mentioned. Actually, Euler was the first to calculate these elliptic integrals. Okay? Only that, of course, then Legendre has taken this on a systematic footing. He has classified the types of elliptic integrals, and they were systematically studied by Abel, right? Okay, but already Euler looked at this at the following example. Okay, at the following example. At the example of inversion of such similar integrals. Here, what we have here under the square root is a polynomial of degree 2. But we could put, instead, we could put a polynomial of degree 3 or 4 or 5 or 6, whatever instead, right? Well, let's start with 2 and 3, or 3 and 4. Because these are the cases that give you elliptic functions. Because the higher ones give you hyperelliptic functions. Okay? So let's start with the cases 3 and 4. And of course, you have to look at the roots of these polynomials, and you get the more symmetric picture if you have a polynomial like that for which has symmetric roots, right? And this was exactly the example at which we were looking last semester. If you remember, I was drawing you the Riemann surface for the following polynomial. This was exactly the example we discussed, the Euler's example. So the integral from 0 to x of dt over 1 minus t square, 1 minus k square t square. Right? Well, I do not remember actually whether k or k square is called the modulus. K or k square may be the modulus. I do not remember. I should know, but I do not. No. Just a second. For some constant k, right. Right. But, well, k is called the modulus, yeah, the k. Okay, the parameter k is called the modulus in this case. Okay, and so now let's invert this integral. This is exactly what these guys, starting with Euler, were doing. Okay, of course, Euler has written the addition formulas for such integrals, right? We have seen it last semester. Okay, and let's invert this integral. This means that x is equal to Sn of u. Sn is almost a sine. It is a higher version of sine. This is one of the basic Jacobi elliptic functions. Okay. One of the Jacobi basic elliptic functions. Well, it is. Actually, it is odd. So what you wish to construct, now the cosine. Well, what would you define as the cosine? Now you tell me. You tell me. Now you should guess.
Cosine squared.
Right. is equal to,
A squared.
no, is equal to 1. But the second one is the following one. K square sine square plus dn u square is 1. So this means that now you have not two functions, basic trigonometric functions. You have three basic elliptic functions, Sn, Cn, and dn. Well, this is sine, cosine, well, and d follows. Okay. Of course, this is the notation. This is not the notation used by Jacobi himself. This is a subsequent thing. Jacobi himself used different notation that we do not discuss. But these are the three basic Jacobi elliptic functions. One is the analog of sine, and two analogs of cosine. Right? But of course, in the textbooks, in the old textbooks, which discuss applications to geometry and physics, differential equations, physics, classical mechanics, and so on, of course, they have more Jacobi elliptic functions, which are either the inverses of this, like you guess what is ns of u. Right? And of course, you guess what is SC of u, right? Well, this is 1 over Sn of u, and this is Sn of u over Cn of u, and so on. You can define whatever, how many, 12 of those? Or? And now imagine that you are at a sort of very advanced elementary school, like Cambridge University, and at the time of Hardy and Littlewood. And your teachers, they want to give you, test problems to check your skills, computational skills. So what they do, instead of problems on trigonometry that you have seen with only two basic trigonometric functions, sine and cosine, and the field of functions on a circle, they give you this. Okay, they give you this. They give you problems on Jacobi elliptic functions. Okay, and they ask you to prove identities for Jacobi elliptic functions. Like, for instance, what would be the analog of the addition formula? Right? Well, I will show you some. Because, of course, we are not studying the elliptic trigonometry. Well, we could, but probably, well, actually, I looked at this as a child because at my home there were textbooks, handbooks of mathematics for people in engineering and physics, and they were full of the formulas of the type. So one of the books with which I was playing as a child was Watson, the Theory of Bessel Functions. Have you seen this book? Oh, it's this size, 2 volumes. Very nice. It's full of formulas of the type I'm writing you now. Okay. But usually, mostly, mathematicians nowadays were not playing with this kind of stuff until recently. Now that it's coming back. But of course, now it's coming back on a different, sort of on a different base, because now we can use computers. Of course, now, at that time, what was amazing was not that people were able to write such formulas, but that the fact that they were able to write such formulas by hand. Of course, nowadays, everyone can write such formulas by his computer. If you install Matematica or Maple or something similar, you can easily write all such formulas. So this means that actually all usual tests that require computational skills, they became completely meaningless. I'm going to speak on that tomorrow, actually, at the Conference on Mathematics Education. Okay, but here are some formulas that are, well, I've lost them. Addition formulas. For Jacobi elliptic functions. Okay? Well, typical. In the meantime, you recall the addition formula for something like this. And compare now. Okay, theorem. Well, Jacobi. Well, and now imagine that you are given to derive some corollaries of these formulas for your exam, for these functions and the inverse functions. So Sn of x plus y is equal to Sn of x, Cn of y, dn of y. Well, and you can guess why. Because there is the fourth degree polynomial in the denominator. Right? Plus Sn of y, Cn of x, dn of x over 1 minus k Sn of x square Sn of y square. Okay? Huh? Does it ring a bell? Well, look here. Right? So Cn of x plus y, well, this should be even, yes? Right?
Easier.
Huh?
Even easier.
No. No, you will see why. So it will be Cn of x, Cn of y, minus Sn of x, Sn of y, dn of x, dn of y, over, well, over the same, of course. 1 minus k Sn x square. Sn y square. And now dn of x plus y, make your guess. Well, obvious. After you have this, you know what's. Got it? Huh? Well, of course, you can replace k squared by 1 by replacing 1 by 1 over k squared, so it's complete symmetry. Dn of x, dn of y, minus Sn of x, Sn of y, Cn of x, Cn of y. 1 minus k square Sn x squared Sn y squared. And now imagine you are given a sort of perverse mind to proceed. To look at the corollaries of this, you can sort of develop the elliptic trigonometry in the same style as from that point. Of course, with all geometric applications and so on. And of course, the classical treatments, they are impossible to read because they were like just in the school style, only that sort of much fancier, much more computational. There is a very beautiful modern exposition, which is actually a diploma paper. Very beautiful diploma paper at the University of Durham. Okay, so it's not even a PhD thesis by Jamie Snape. It's called Application of Elliptic Functions in Classical and Algebraic Geometry, and it's a diploma paper. So, diploma, where you can write a beautiful modern treatment of that. A diploma paper, University of Durham. Whatever. I can send it to you, actually. It starts with the following beautiful quotation of Jean-Pierre Serre. It strikes me that mathematical writing is similar to using a language. Well, Serre had a talk on that. Maybe I've mentioned to you, where he was discussing mathematical mistakes. I mean, not mathematical, mistakes in mathematical writing. Like confusion of principle and principle. Principle bundle on a moral base, or and things like that. Moral principle, whatever. So it strikes me that mathematical writing is similar to using a language. To be understood, you have to follow some grammatical rules. However, in our case, nobody has taken the trouble of writing down the grammar. We get it as a baby does from parents, by imitation of others, mathematical exposition. Some mathematicians have a good ear, some not. That's life. Because no one teaches us how to write papers, actually. Well, maybe for papers, yes, but not for... Nobody teaches us how to teach, for instance. Okay, this is where the theory was at the time of Jacobi. But of course, it's not finished there, and we still have 8 minutes to start the Weierstrass theory, because this was a real breakthrough. Okay, it's much easier, because Weierstrass had the advantage of being able to look at that from the viewpoint of Riemann's theory of meromorphic functions. So he knew the following. That two functions, two elliptic functions, they coincide if they have the same poles and the same zeros with the same multiplicities. Or otherwise, they coincide up to a multiplicative constant. Okay? So theorem, corollary of Riemann's theorem is that if f and g are elliptic functions, to the same lattice gamma, okay, with the same zeros and poles of the same multiplicities. Then they coincide up to a multiplicative constant. Right? And of course, you have only to count, you have to count the multiplicities of zeros and poles in the fundamental region. But that's not a good idea to take the usual fundamental region. Why? The fundamental parallelogram. You know why it's not a good idea? Because your function can have zeros or poles on the boundary. So what you do, you have to move this region a bit. Okay, you have to move it a bit to translate it in such a way, because there are finitely many inside and on the border. So you can move the fundamental region in such a way that there are none on the border. And then you can use, of course, the Cauchy theorem. Okay? And then you know that by the Cauchy theorem, by the periodicity, the integral along this cancels with the integral along this. And the integral along this cancels with the integral along this, because they are passed in opposite directions. By periodicity, they cancel. Okay, this means that the integral over the boundary is 0 of such a cell where all the poles and zeros are inside. The integral is 0, meaning then the sum of residues is 0. And by Riemann's theorem, that's the only restriction. So the function with a given number of zeros and poles exists, of given multiplicities, exists if with the only linear restriction that the sum of the residues along the boundary is 0. That's the only restriction. Okay? And so, in other words, an elliptic function is determined by these guys, and plus, well, up to a multiplicative factor. Or what is the same is determined by the principal parts. Well, you remember what's the principal part of a Laurent series? The negative part of the Laurent series at some point. Okay, by the at all poles. Okay, so this means that an elliptic function cannot have a simple pole. It has at least 2 poles counted with multiplicity. Okay, and if the residues cancel, then such a function exists. Okay, so what are the simplest cases? The simplest case is when you have a double pole with residue 0. Okay, and that's called the Weierstrass P function. So the simplest function to exist is the function which has one double pole, and of course, by additive constant, you can move this pole to 0. You can assume that your poles are at the lattice points, right? And by multiplicative constant, you can assume that the lowest coefficient is equal to 1. And the coefficient, the residue is 0, and the free term is 0, because you have moved it to 0. Okay, so definition the Weierstrass P function, well, it should be a handwritten P. Of course, you can write P function. What would you prefer me to do? But traditionally, of course, in the books, they print P like that, handwritten. Right? The Weierstrass P function is to gamma is the elliptic function, well, the only elliptic function to gamma with double poles at lattice points of gamma, no other poles, and principal part, well, Laurent expansion. At 0, that starts as follows: 1 over z square plus, well, residue is 0, right? No residue. Free term is 0. So the next term is C1z plus C square z square plus etc. And there is only one such function. Here it is. Huh?
This C1, C2, etc.
Exactly, yes, and they are related to the modular invariant. Of course, yeah, right. So they are uniquely determined by the lattice gamma, right? And they will be the coefficients of the corresponding elliptic curve of the equation. Okay, right. Well, such a function exists by Riemann's theory. Of course, what Weierstrass did, he has calculated the coefficients. Right? Riemann's theory predicts that such a function is unique. Existed is unique. But what it is? Well, it is as follows: 1 over z square plus the sum over omega in gamma minus 0, 1 z minus omega square minus 1 over omega square. And that's, of course, Weierstrass. Well, does this function generate, and we have to finish here, does it generate the field of modular, the field of elliptic functions? No, because it's even. We have to construct its odd function. So what we should do? Take the derivative, and that's it. A derivative, and then, of course, the square of the derivative is an even function. And so by uniqueness, it is a rational function of the P function itself. And you get an algebraic equation. That's it. Okay, so the field of elliptic functions is generated by the Weierstrass P function, its derivative, and they satisfy an algebraic equation of degree 3. They are related by an algebraic equation of degree 3 that defines an elliptic curve. And that's it. So which one is easier? Inverting an integral or this? But of course, here we have an advantage of a hindsight, you know, of advantage of the real topological theory of complex functions, right? Of the idea of Riemann surfaces. And this has advantages.
Yeah, does have.
Well, what do you mean? It's more directly related to applications, because what occurs in the actual applications to elementary geometry and to classical mechanics, of course, are these functions, right? But if you are algebraically oriented, of course, this is much, much easier. Yeah. right? Okay, so next time we proceed with this and introduce the connection with the modular functions, because that's really where Jacobi was heading, because he was trying to, and he did that actually, to establish the formulas for the number of representation of integers by sums of squares. This is how the modular functions arose. Okay, thank you. It's all for today. I think we have to finish here. Yeah, right.